There's something deeply unsettling about the universe when you look at it carefully enough. Not unsettling in a mystical or supernatural way, but unsettling because the mathematics forces you to conclusions that seem impossible, yet appear to be true. I've spent years thinking about one particular aspect of cosmology that bothers me more than almost anything else in physics. It has to do with what happens when you try to understand the universe at the largest scales, and what the equations tell us must be out there. Let me start with a simple observation. When you look up at the night sky, you see stars, thousands of them. If you're far from city lights, with a telescope, you see millions. With the Hubble Space Telescope, billions. And here's the first strange thing. The farther out you look, the farther back in time you're seeing. Light travels at a finite speed, about 300,000 kilometers per second. That sounds fast. But the universe is so large that light from distant objects takes billions of years to reach us. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. When you look at Andromeda, you're seeing it as it was 2.5 million years ago. More distant galaxies appear as they were billions of years ago, when the universe was younger. The most distant objects we can see, quasars and ancient galaxies, show us the universe as it was more than 13 billion years ago, less than a billion years after the Big Bang. Now here's where it gets interesting. In 1929, Edwin Hubble made a discovery that changed everything. He measured the distances to various galaxies and their velocities, how fast they were moving away from us. He found a relationship. The farther away a galaxy is, the faster it's receding. This is Hubble's law. The recession velocity is proportional to distance. This tells us the universe is expanding, not expanding into anything. Space itself is expanding, carrying galaxies along with it. If you run this expansion backward in time, you find that everything was closer together in the past. Run it back far enough, and you reach a point where all the matter and energy in the universe was compressed into an incredibly hot, dense state, the Big Bang. The evidence for this is overwhelming. The cosmic microwave background radiation, the afterglow of the Big Bang, fills the entire universe. We can measure it precisely. Its temperature is about 2.7 Kelvin, and it has tiny variations from point to point that tell us about the density fluctuations in the early universe that eventually grew into galaxies and clusters of galaxies. The predictions of Big Bang cosmology match observations to extraordinary precision. But now let me tell you what disturbs me. When we measure the expansion rate of the universe, the Hubble constant, and when we measure the total amount of matter and energy in the universe, we find something completely unexpected. The universe is not just expanding, it's accelerating. The expansion is speeding up. This was discovered in 1998 by two independent teams studying distant supernovae. Type Ia supernovae are excellent distance indicators because they all have roughly the same intrinsic brightness. By comparing their apparent brightness to their known intrinsic brightness, you can calculate how far away they are, and by measuring the redshift of their light, you can determine how fast they're moving away from us. What the teams found was shocking. Distant supernovae were dimmer than expected, which means they're farther away than they should be if the expansion were slowing down due to gravity. The only way to explain this is if the expansion is accelerating. Something is pushing the universe apart, overcoming the attractive force of gravity. We call this something dark energy, and here's the disturbing part. When you calculate how much energy density you need to produce the observed acceleration, you find that dark energy makes up about 68% of the total energy content of the universe. Dark matter, the invisible matter we infer from its gravitational effects, makes up about 27%. Ordinary matter, everything we can see, all the atoms in all the stars and galaxies, makes up only about 5%. Think about that. 95% of the universe is made of things we can't see and don't understand. We've given them names, dark matter and dark energy, but these are just labels for our ignorance. We don't know what they are. We have some ideas, but no confirmed theory. Dark matter, at least, behaves in ways we can partially understand. It clumps gravitationally. It forms halos around galaxies. Its gravity bends light, producing gravitational lensing effects we can observe. We can map where dark matter is in the universe by looking at how it affects visible matter and light. Several candidate particles might be dark matter: WIMPs, axions, sterile neutrinos. Experiments are searching for these particles. So far they haven't found them, but at least we have plausible theories. Dark energy is worse. It doesn't clump, It's uniformly distributed throughout space. It has negative pressure. It pushes things apart instead of pulling them together. The simplest explanation is that it's the energy of empty space itself, what we call vacuum energy, or the cosmological constant. Quantum field theory predicts that even empty space should have energy because of quantum fluctuations. Virtual particles pop in and out of existence constantly. These fluctuations contribute to the energy of the vacuum dot. But here's the problem. When you calculate what the vacuum energy should be using quantum field theory, you get a number that's about 10 to the power of 120 times larger than the observed dark energy density. This is the worst prediction in the history of physics. We're off by 120 orders of magnitude. Something is clearly wrong with our understanding. Either quantum field theory is wrong in some fundamental way when applied to cosmology, or there's some mechanism that cancels out almost all of the vacuum energy, leaving just the tiny amount we observe. Nobody knows what this mechanism could be. This is called the cosmological constant problem, and it's one of the deepest unsolved problems in theoretical physics. Let me make this concrete. The observed dark energy density is about 10 to the minus 29 grams per cubic centimeter. That's incredibly small. A cubic centimeter of space contains less than a trillionth of a trillionth of a trillionth of a gram of dark energy. But quantum field theory predicts it should be 10 to the 91 grams per cubic centimeter. That's not just wrong. It's absurdly wrong. If the vacuum energy were actually that large, the universe would have expanded so fast that no structures could ever have formed. No galaxies, no stars, no planets, no us. So we exist because the vacuum energy is small, but we have no explanation for why it's small. This isn't like other fine-tuning problems in physics, where you can say, well, maybe there's some symmetry or some principle that explains it. We've looked for such principles. They don't seem to exist. The vacuum energy is what it is, and we don't know why. Some physicists have proposed the anthropic principle as an explanation. The idea is that if the vacuum energy were different, we wouldn't be here to observe it. In a multiverse, a collection of many universes with different physical constants, only universes with small vacuum energy would develop structures and life. We necessarily find ourselves in one of those universes because we couldn't exist in the others. I've never liked this argument. It feels like giving up. It doesn't explain anything. It just says, well, that's the way it is. But I have to admit, nobody has come up with a better explanation. And the anthropic argument does make one testable prediction. It predicts the vacuum energy should be as large as possible while still allowing structure formation. Too large. And galaxies never form. The observed value is close to this maximum, which is at least consistent with the anthropic explanation. But consistent isn't the same as confirmed. Now let me tell you what really disturbs me when I think about dark energy and the future of the universe. The universe is accelerating. As time goes on, distant galaxies are moving away from us faster and faster. Eventually they'll be receding so fast that their light can never reach us. They'll disappear beyond our cosmic horizon. Right now we can see objects up to about 46 billion light-years away. That's the current size of the observable universe, not 13.8 billion light-years, which is the age of the universe, but 46 billion because space has been expanding while light travels. As the universe continues to accelerate, this observable region will actually shrink. Distant galaxies will cross our cosmic horizon and disappear from view. In about 100 billion years, all galaxies outside our local group, the few dozen galaxies bound together by gravity, including the Milky Way and Andromeda, will be gone. Astronomers in that distant future will look out and see only their local group surrounded by darkness. They won't be able to see the cosmic microwave background because it will be redshifted to infinitely long wavelengths. They won't see distant galaxies. All evidence of the Big Bang and the expanding universe will be gone. Think about what this means. Those future astronomers will have no way to discover that the universe is expanding. They'll have no evidence for the Big Bang. They'll think they live in a static island universe surrounded by infinite empty space. Everything we've learned about cosmology in the last century will be unavailable to them. The universe will have erased its own history. Are we in a privileged time? Is it just coincidence that we live in an era when the universe is old enough for stars and planets to form, but young enough that we can still see the evidence of the Big Bang and measure the expansion? Or have we already lost crucial information about the universe's history that was observable at earlier times? This question bothers me because it touches on something fundamental about science. We assume that by observing the universe and doing experiments we can figure out the laws of physics. But what if the universe doesn't give us all the information we need? What if crucial evidence has already disappeared beyond our cosmic horizon or hasn't yet come into view? How would we know? There's another disturbing aspect to the accelerating expansion. In quantum field theory, the vacuum isn't truly empty, it's filled with quantum fields in their ground state. These fields can have fluctuations, temporary violations of energy conservation allowed by the uncertainty principle. If the vacuum energy is related to these fluctuations, then vacuum isn't the same everywhere. It can have different energy densities in different regions. This leads to the idea of eternal inflation. In the early universe, space was expanding exponentially fast, inflating. This inflation explains several features of the observable universe, like why it's so uniform on large scales. But if inflation can start, it might not stop everywhere at once. Some regions stop inflating and become universes like ours. Other regions keep inflating and spawn more regions that stop inflating, creating more universes. The process never ends. If eternal inflation is correct, then our observable universe, everything we can see, stretching 46 billion light-years in all directions, is just a tiny bubble in an infinitely larger inflating space filled with countless other bubbles. Each bubble could have different physical constants, different particle physics, even different spatial dimensions. We'd be living in one bubble among an infinite number of bubbles in an eternally inflating multiverse. This idea disturbs me for several reasons. First, it's not clear the theory is testable. If other universes are beyond our cosmic horizon, we can never observe them directly. We can only infer their existence from theoretical arguments. That's not how physics usually works. We test theories by making predictions and checking them against observations. If a theory predicts things that can never be observed, is it really science? Second, the multiverse idea undermines the predictive power of physics. In our universe, we observe that the electron has a particular mass. The fine structure constant has a particular value. The cosmological constant is small. We'd like to explain these values by deriving them from a deeper theory. But if there's a multiverse where these constants vary, then there's no unique prediction. Everything that can happen does happen somewhere. The only constraint is anthropic. We observe the values we do because those values allow us to exist. I don't like this. It feels like physics is giving up on explanation and resorting to, well, that's just how it is in our bubble. But I'm also honest enough to admit that nature doesn't care what I like. If the universe actually is a multiverse, then that's reality, and we have to deal with it. The question is whether we can find evidence for or against the multiverse hypothesis. There might be ways. If our bubble universe collided with another bubble in the past, it might have left an imprint in the cosmic microwave background, a circular pattern of temperature variations. People have looked for such patterns. They haven't found convincing evidence yet, but the search continues. Another possibility involves the quantum nature of the vacuum. If different regions of space can have different vacuum energies, then quantum fluctuations might occasionally create transitions between these vacua. Our vacuum might not be the lowest energy state. There might be a lower energy vacuum, and quantum tunneling could cause a transition to that lower state. If this happens, a bubble of lower energy vacuum would form and expand at the speed of light. Everything inside the bubble would be destroyed. Atoms would disintegrate. Particles would transform because the physics inside the new vacuum would be different, and we'd have no warning. The bubble wall would hit us at the speed of light, so we couldn't see it coming. Is our vacuum stable? We don't know for certain. The stability depends on the precise values of the Higgs boson mass and the top quark mass, which we've measured at the Large Hadron Collider. The current measurements suggest our vacuum is metastable, not the absolute lowest energy state, but long-lived. The probability of tunneling to a lower vacuum is extremely small. The expected lifetime of our vacuum is vastly longer than the current age of the universe. But vastly longer doesn't mean infinite. It's possible that somewhere in the universe right now a bubble of new vacuum is forming and expanding, heading toward us at the speed of light. We'd never know until it arrived. This is called vacuum decay, and it's one possible way the universe could end. Let me be clear. This is extremely speculative. We have no evidence that vacuum decay is happening or will happen. The calculations suggest it's extraordinarily unlikely. But the fact that it's even possible, that the mathematics of quantum field theory and cosmology allows for it, is disturbing. The universe we live in might not be permanent. The laws of physics themselves might change. There. Quote, another aspect of deep space that bothers me. and it has to do with black holes. When a massive star exhausts its nuclear fuel, it collapses. If it's massive enough, nothing can stop the collapse. It forms a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. The boundary of a black hole is called the event horizon. Anything that crosses the event horizon is gone forever from the perspective of an outside observer. But from the perspective of someone falling in, nothing special happens at the horizon. They just keep falling until they reach the singularity at the center where the equations of general relativity break down and give infinities. This already bothered me. Infinities in physics usually mean your theory is incomplete. At the singularity, space-time curvature becomes infinite, density becomes infinite, and we need a theory of quantum gravity to describe what's really happening. We don't have such a theory. String theory is a candidate, but it's not confirmed. But then in the 1970s, Stephen Hawking made an even more disturbing discovery. He showed that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. Virtual particle pairs form just outside the horizon. Normally they'd annihilate each other, but near the horizon, one particle can fall in while the other escapes. The escaping particles form what we call Hawking radiation. This radiation carries energy away from the black hole. Over enormous timescales, a black hole will evaporate completely. A solar mass black hole would take about 10 to the 67 years to evaporate. That's unimaginably long, but given enough time, all black holes will disappear. Here's the disturbing part. The Hawking radiation is thermal. It's random, with no information about what fell into the black hole. If you throw a book into a black hole and wait for it to evaporate, the radiation that comes out is just random heat. The information contained in the book, the precise arrangement of atoms, the text on the pages, is gone. This violates a fundamental principle of quantum mechanics called unitarity, which says information cannot be destroyed. This is the black hole information paradox. Either quantum mechanics is wrong, or general relativity is wrong, or our understanding of black holes is incomplete. For decades, physicists have debated this. Some argued information is preserved somehow, encoded in subtle correlations in the Hawking radiation. Others argued information really is destroyed, and we need to modify quantum mechanics. Recent work suggests information is preserved, but in a very subtle way, involving quantum entanglement between the inside and outside of the black hole. The details are still being worked out. But the fact that combining quantum mechanics with general relativity leads to such deep paradoxes tells us we don't fully understand the nature of space-time. And this brings me to the deepest thing that disturbs me about looking into space. The more we learn, the more we realize how much we don't know. We don't know what dark matter is. We don't know what dark energy is. We don't have a theory of quantum gravity. We don't know if the universe is a multiverse. We don't know if our vacuum is stable. We don't know how information escapes from black holes. Every question we answer raises new questions. And some of these questions might not have answers we can ever verify. If other universes exist beyond our cosmic horizon, we can't observe them. If our current understanding requires a theory of quantum gravity, but quantum gravity effects are only important at energy scales, far beyond what we can reach with particle accelerators, we might never be able to test the theory directly. This isn't the end of physics. Far from it. We keep making progress. We keep testing theories against observations. We keep refining our understanding. But we have to be honest about the limits of what we can know. I've always believed that nature is comprehensible, that the universe operates according to mathematical laws we can discover through observation and reason. I still believe this. But I've also learned to accept that comprehensibility doesn't mean easy, and it doesn't mean we'll necessarily find all the answers. The universe is under no obligation to make sense to us. It doesn't care about our intuitions or our philosophical preferences. It is what it is. Our job as physicists is to describe it as accurately as we can, using mathematics and experiment, and to be honest about what we know and what we don't. When I look deep into space, I see billions of galaxies, each containing billions of stars. I see the cosmic microwave background, the afterglow of the Big Bang. I see quasars powered by supermassive black holes. I see gravitational lensing, where the gravity of massive objects bends light from more distant objects. I see all the evidence for dark matter and dark energy and the accelerating expansion. And I see mystery. Deep, profound mystery about the nature of space, time, matter, and energy. This doesn't disturb me in the sense of making me anxious or afraid. It disturbs me in the sense of challenging everything I thought I understood. It forces me to question assumptions I didn't even know I was making. That's what physics does. It takes comfortable ideas and smashes them against reality. It shows you that the universe is stranger than you imagined, and then it challenges you to understand that strangeness using logic and mathematics. The disturbing things about deep space, the dark energy, the accelerating expansion, the possibility of vacuum decay, the information paradox. These aren't reasons to give up or to retreat into mysticism. They're invitations to dig deeper, to develop better theories, to design more precise experiments. They're what makes physics exciting. We live in a universe where 95% of the content is invisible, where space itself is expanding and accelerating, where the vacuum might not be stable, where information might be preserved in ways we don't yet understand. This is disturbing, this is profound, and this is what we get to work on. What we get to try to understand, that quote, "It's what I find when I look too deep into space." Not easy answers, not comfortable certainties, but deep questions about the fundamental nature of reality. Questions that might take centuries to answer. Questions that might change our understanding of everything. That's not disturbing. That's what physics is supposed to be.